How are you? It's been a long time since we have seen each other in the videos. Today, we are starting a new course in solving differential equations, of course. This is Engineering Mathematics 2A, and today we are looking at something called the Laplace Transforms. Right, we are looking at something called the Laplace Transform. What is the Laplace Transform? Right, the Laplace Transform, it is an integral transforms used to solve higher order differential equations. Right? It is used to solve higher order differential equations. How do they solve this differential equation? By turning it to algebraic partial fractions. Here, when we solve differential equations using the Laplace transform, we are taking this thing and transforming it to other parts of this world, and it's going to tend to be an algebraic partial fraction. It is easier to solve because you're going to use partial fraction decomposition at the end. It is going to be our last video on Laplace transform when we solve differential equations and taking the inverse. Right, so here the idea is when we take the Laplace transform of f of t, we will get f of s. Right, we are transforming from time to s domain. So whenever you take the Laplace transform, you're always going to take your Laplace transform from t, and your final answer must be in terms of s. Do you understand that? And what you need to know is that the Laplace transform of f of t is an improper integral from 0 to infinity of e to the power negative st of f of t dt. Right. One thing that you need to know here is that your f of t must be an exponential order. What do we mean by a function who is an exponential order? It is bounded by m e to the power c. So a function which is always bounded by this, it is an exponential order. Right, do you understand that? And you need to know that S, it is your what? It is your complex parameter, which means if S is a complex parameter, we say that S is an element of complex numbers. So S is equals to alpha plus j beta. From now on, we are not going to use A and B, but let us just have this idea of alpha and beta, right? And for this to work, the integral above must converge as it approaches infinite. So what do you mean by that? As t approaches infinite, the integral must converge to what? To 0. Do you understand that? The integral must converge to 0. And also about the thing of f of t, we do not care about f of t, but it must exist. This is another thing that most people do not know, that f of t must exist between t is an element from 0 to positive infinite. Whenever we take the Laplace transform, just know that you take the Laplace transform from 0 to infinite. Do you understand that? So I think you will get this later, right? But bear with me for now. Now we have seven functions that you need to know to take the Laplace transform of, right? The first one, if f of t is equals to a, and a, it is a constant, then the Laplace transform of a, it is a over s. Do you understand that? And then if f of t, it is e to the power kt, then again that k, it is a constant again, then the Laplace transform of e to the power kt, it's always going to be 1 over s minus k. Now this thing will only work, this formula will only work for k which is positive. Do you understand that? For k which is positive. Now if we take the Laplace transform, if f of t, it is e to the power negative k, then the Laplace transform of e to the power negative kt, it is 1 over s plus k. Do you see the difference? This one, it is k, it's greater than 0. Here, k, it is what? It is less than 0. Do you understand that? Another thing that you need to know is that if f of t, it is t to the power n, which is an algebraic term raised to an exponent, then the Laplace transform of t to the power n, it is what? It is n factorial divided by s to the power n plus 1. right? And then if f of t, it is the sine of a t, where a is the constant, then the Laplace transform of sine a t, it is what? It is a divided by s squared plus a squared, like that. And then if your f of t, it is the sine of a t, then the Laplace transform of sine a t, it's going to be a over s squared minus a squared. So for sine, it's going to be minus. For sine, it's going to be minus, but for sine, it's going to be plus. And the last two is that if f of t, it is cos, if f of t, it is cos a t, then the Laplace transform of cos a t, it's going to be s over s squared plus a squared, and then f of t, it is cos a t, then the Laplace transform of cos a t, it is going to be s over s squared minus your a squared. Do you understand? So functions that you see here, these are the only functions that we do have the Laplace transform of. Do you understand that? These are the only functions that we do have the Laplace transform of. But if you do more research on the Laplace transform, you'll have more functions. But for the scope of the Laplace transform for students, this is the Laplace transform that we are going to teach you. Right. Now, my work is to give you the proof of each of these. So in this video, we are going to prove each of these. Do you understand? We are going to prove each of these. But first, let us start. Now, we call this the method of the first principles. So here we're using the definition that states that the Laplace transform of f of t is equals to an integral from 0 to positive infinite of e negative st of f of t dt. We are using this analogy here, so it's called the method of the first principle. So if you find this thing in a major test or in an exam, just know that whenever they are asking you use the method of the first principle, you are using this equation here. Right. So the first one. So what is the Laplace transform of a? So a can be any number. So we are going to say from 0 to infinite, a times e to the power negative st dt. Another thing that you need to notice here is that we cannot just substitute infinity in. That is another problem that we have. So since this integral is improper, this is an improper integral. You're supposed to know it from calculus 2. This is an improper integral, and to evaluate the improper integral, we need to replace infinite with the different letter. Do you understand that? We need to replace infinite with the different letter to evaluate it. So the integral will become now equals to, because a is a constant, we can just take it out, and then we are going to take the limit of the integral as k approaches infinite. The reason we are doing this is because we have infinite there, so we cannot just integrate it if you have an infinite there, right? So now I'm going to integrate it from 0 to k e to the power negative st dt. So whenever you have an integral that has an infinite, you cannot just integrate it, but what you can do, you can just take a limit of that integral as a particular letter reaches infinite, right? So now we need to integrate this part. So now I still have a times the limit as k approaches infinite in bracket. What is an integral of e to the power negative st? What you need to know is that since we are integrating in terms of t, this s here, it is a what? It is a constant. It is a constant. So we can just simply divide it by remembering this rule. Remember that the integral of e to the power ax dx, it is always what? 1 over a e to the power ax plus c. You still remember this from calculus 2, right? So what is an integral of that? It's negative 1 over s. It's negative 1 over s e to the power negative st. Now this thing is between 0 and k. So it's a times an integral, a times the limit as k approaches infinite in bracket. Now we substitute k there, so it's negative 1 over s e to the power negative st minus k s, and then plus 1 over s e to the power 0, which is the same thing as 1. Right. Now when you take the limit, I'm just going to explain it as smooth as I can because I don't want you to be misled with the calculations here. Now when you take the limit, I'm just going to say, okay, this is a in bracket. When you take the limit here as k is approaching infinite, can you please look at this graph here? What do you see? You see an exponential graph that is decreasing, right? So I'm just going to write them here. You see e to the power negative ks. If you draw this graph, it is a graph that will resemble a decreasing function, as a decreasing function. And the Laplace transform starts here from 0 to infinite. Now, you can clearly note that this graph, as it approaches infinite, it's going to approach the x-axis, right? Because the graph is approaching the x-axis, the x-axis, y value corner, it is what? The y value of the x-axis, it is always 0. Or what you can see is that since the area of this graph decreases as you approach infinite, the limit of this thing here would be 0, right? So this part, this entire part, it's 0 because of that fact. So now I'm left with 1 over s, which is the same thing as a over s. So the Laplace transform of any constant, it's always like that. So the Laplace transform of 4, it is 4 over s. The Laplace transform of negative 7, it is negative 7 over s. The Laplace transform of pi, it is pi over s. The Laplace transform of e, it is e over s. All of these numbers here are constant. The Laplace transform of 1 over 2, it is 1 over 2 over s. Or you can just say it's 1 over 2s if you're writing it in a mathematical way. Any questions? If you have questions, you just go down to the comment section. So we have proved that the Laplace transform of any constant, it is given by that. Now we are going to prove that the Laplace transform of e to the power k, it is that. Your homework will be proving this one. So what is the Laplace transform? What is the Laplace transform of e to the power k t? So find the Laplace transform of e to the power kt, we need to use the formula from 0 to infinite e to the power kt times e to the power negative st dt. From our given problem here, you can see that these two bases are the same, alright? Since these two bases are the same, we can multiply the bases and do what with the exponent? Add the exponents. So I'm going to have an integral from 0 to infinite of e to the power kt minus st dt, like that. There was a thing that I said here, that the Laplace transform must converge to 0. For the Laplace transform to converge to 0, you must always have an exponent of e. Listen to me. For the Laplace transform to converge, your exponent of e must always be what? Be negative. Do you understand that? The Laplace transform of e must always be negative. So what I am going to do next, from 0 to infinite e, I'm going to take out the highest common factor here of a negative. So if I do that, I'm going to have a negative in bracket s minus k t dt. Do you understand that? So for the Laplace transform to converge, the e must have an exponent of a negative for this to converge. Why is that? Remember the graph that I drew? There was this graph here. This graph, since the Laplace transform starts from x is equals to 0 towards infinite, this graph decreases. It mimics y is equals to minus ax. Since the graph of e to the power minus is a decreasing function, it's going to converge to 0 at the end. So that's why we must always have an exponent of a negative e. Right. So another thing that you need to notice is that s minus k, it is a constant. We need to use this theorem here to integrate that. So how will we use the theorem? Now I have forgotten that we need to do what? Now we need to integrate. We are going to say it is a limit as a approaches any letter that you prefer to infinite, integral from 0 to a e to the power negative s minus kt dt. Right. So when we integrate this part, we are going to have below the limit as a approaches 0 on negative 1 over s minus k times e to the power negative s minus k t between 0 and a. Right, substitute a in. I'm going to have the limit as a approaches infinite on negative 1 over s minus k e to the power negative s minus k times a, and then if you substitute 0 there, I'm going to have plus 1 over s minus k. Again, when you substitute infinity to e that has a negative exponent, this entire integral here will become what? Will become a 0. So your final answer, it is what? The final answer, it is 1 over s minus k. Right. An example will be that the Laplace transform of e to the power 4k 40, it is always 1 over s minus 4. The Laplace transform of e to the power negative 7t, it's going to be 1 over s plus 7. Just keep that in mind. When the exponent is positive, here I'm going to get a negative. When the exponent is negative, here I'm going to get a positive. Right. The second one, the third one, by the way, the third one uses something called mathematical induction. It uses that particular thing. It's mathematical induction. Now, mathematical induction, it is a sense of you know what is going to happen at the end. Do you understand that? You know what is going to happen at the end. Now, I'm just going to give you one. That is going to be used. If I say n, you will not understand the meaning, right? But if I say times n minus 1, times n minus 1, again, you don't understand. But times n minus 2, you will not understand. The moment I add the third one, you will notice that this means n factorial. This is the pure definition of n factorial, which is n times n minus 1, n minus 2, n minus 3. I'm not going to teach you permutations here, but this is the use of mathematical reduction and induction. You need to know that mathematical induction and reduction. Oh, you need to notice the pattern that this thing is going. Right. So please keep that in mind. Now, what I am going to do, I am going to take the Laplace transform, not the z, the Laplace transform of t to the power n, which is the integral from 0 to a t to the power n times e to the power negative st dt. I told you last year in class that I'm not going to use the long method of integration by parts, but I'm just going to use the one that has the table. So integration by parts here, it's the most crucial thing that you need to know. Right. So if you use the table here, so I'm going to have s d I plus the derivative is t to the power n, and I, it is e to the power negative st. I'm just going to remind you, how did I choose this? It's L-I-A-T-E. This thing is used from left to right. You go to your problem. In your problem, you have two functions. You have an exponential function, which is e, and you have an algebraic function, which is t to the power n. Now, from left to right, which letter comes first? From left to right, which letter comes first? A or E? It is A. Since A comes first, I'm going to substitute it on D. The letter that comes the last, I'm going to substitute it on I. That was the procedure. The next thing that you need to do, I'm going to put minus the derivative of that. It's going to be n times t to the power n minus 1. The integral of that is negative 1 over s e to the power negative s. Continue doing, plus it's going to be n times n minus 1 t to the power n minus 2. It's going to be 1 over s squared e to the power negative st. If you continue doing it, I'm going to have minus 1 minus n times n minus 1 n minus 2 t to the power n minus 3 1 over s cubed e to the power negative st. Right, so what is the idea then? Because we will continue doing the same thing, I'm just going to substitute it. So now I have negative 1 over s t to the power n e to the power negative st plus 1 over s squared times n minus 1 t to the power n, no, times n times t to the power n minus 1 e to the power negative st plus 1 over x squared s cubed n times n minus 1 t to the power n minus 2 e to the power negative s cubed, and so on. This thing will continue forever. But what you can notice is that when t approaches infinite, the thing becomes 0 for e, and it goes 0 when t is equals to n. So what goes on really is that you are going to have something like n times s times n minus 1 times s times n minus 2 times s times n minus 3 times s times, and so on. If you look at the numerator, you have something called the n factorial divided by, when you look at the denominator, you're going to have n plus 1 s to the power n plus 1. So this is the Laplace transform of t to the power of an exponent. So an example will be provided by saying the Laplace transform of t, it is 1 over s squared. The Laplace transform of t cubed, it is 6 over s to the power 4. The Laplace transform of t squared, it is 2 over s cubed. Right? Now, I'm just going to pose a question. What is the Laplace transform of t to the power half? this thing will be 1 over 2 factorial divided by s to the power 1 over 2 plus 1. Now 1 over 2 factorial, it is root pi over 2. Use something called the gamma function to know how to calculate that. So this is the proof behind the thing, right? And the next proof, I want you to remember. I will want you to remember that E J A T, it is the same thing as EJT is the same thing as the cos of AT plus J, the sine of AT. And cos, it is the real part of that. So the real part of EJE, it is cos of AT. And then sine, it's the imaginary part of that. So the imaginary part of EJAT, it is the sine of 8. I think that is good. So when we are doing the proofs of sine or cos, both of them will show up in the equation. So do not be surprised when they do show up, right? So let us find the Laplace transform. Let us find the Laplace transform of cos AT. So it's going to be an integral from 0 to infinite, of cos AT e to the power negative st dt. Now the first proof that I'm going to use this analogy here. Alright, I'm going to use that analogy there. So what I'm going to use here, I'm going to say, okay, fine. I'm going to say the limit as k approaches infinite on the integral from 0 to k. And I am going to write cos in terms of e. How I'm going to write cos in terms of t? I'm going to use this analogy here that cos is the real part of e to the power j. Sorry. So I'm going to say the real part of EJAT times e to the power negative st dt, like that. And then I'm going to have k, the limit. I'm going to have the limit as k approaches infinity of an integral from 0 to k, re in bracket. These two will multiply, resulting in e to the power JAT minus ST dt. By now you know that for these to converge, you need to have an exponent of negative s. So the limit as k approaches infinite on an integral from 0 to k of re in bracket e to the power negative s minus JAT dt. How do we integrate this? We use this analogy here that the integral, I need to use this space, it's too much. We need to use this analogy here, that the integral of e to the power ax dx is the same thing as 1 over a e to the power ax plus c. So by doing that, I'm going to have the limit as k approaches infinite on the real part of 1 over s, negative 1 over s minus ja between 0 and k. Right, e to the power negative s minus ja t between 0 and k. Now if you substitute k, you know that this thing is going to be 0, right? So I'm going to have the limit k as it approaches infinite on the real part of 1 over s minus j. By now you know that you cannot have this j here. So what I'm going to do, I'm going to multiply by the conjugate of the denominator on the numerator and the denominator. So can I please remove this dt? So now I have re in bracket 1 over s minus aj times s plus aj divided by s plus aj, which is re in bracket s plus aj in bracket. When you multiply this with that, I'm going to have s squared plus a squared. You can do FOIL and then please separate it. If you separate it, I'm going to have s over s squared plus a squared plus j in bracket a over s squared plus a squared. It turns out, since we have written this re, we are saying that you are choosing the real part of the solution. So the Laplace transform of cos at, it is s over s squared plus a squared, and the Laplace transform of sine at, it is a over s squared plus a squared. If you wrote im instead of re, you would have been choosing this one. Right, so this is the Laplace transform. So I'm not going to give you the other one, but you can use integration by parts here. You can use integration by parts. So the Laplace transform of cos for t, it is s over s squared plus 16. The Laplace transform of sine for t, it is 4 over s squared plus 16. Can you please note this thing down, these two? You see that the 4 is here, we have a square of the 4 there. So what about if you have 1 over s squared plus 16? Will you say this is the Laplace transform of sine 4? No. You cannot say that. It's totally wrong. Right. And this one is your homework. Find the I'm just going to answer them in class. Find the Laplace transform of cos at and the Laplace transform of sine 18. Thank you so much. Bye.